in applications. Last year, we organized the first edition of this conference, QFTA 2019, in October 2019, and we were able to physically host all delegates on campus. This year, due to the pandemic, we've had to host the entire conference online. Nevertheless, we have a wonderful lineup of very distinguished speakers, and I'm sure you will enjoy the forthcoming talks. This year, especially, a large number of our alumni are giving talks. These are our own BSMS students who are now doing a PhD, or our own PhD students who are now postdocs, and in some cases, faculty elsewhere. So we look forward to catching up with all of them through their talks. I now request Director IISER Mohali, Professor Gowrishankar, to inaugurate QFTA 2020 and say a few words.
Thank you, Professor Kavita. I hope I'm audible to all the participants.
Yes,
you're audible.
So it gives me great pleasure on behalf of the Institute to welcome all the participants to this online conference, QFTA 2020. And I'm also grateful to my senior colleagues who have taken the trouble of organizing this meeting under these fairly difficult conditions. I'm confident that the meeting, despite these difficulties, will be a very successful and useful one for both the established researchers and the students who are registered to participate in it. It also gives me great pleasure to say that as an institute, IISER Mohali is well placed to host this conference for the amount of interest that is present amongst the faculty working here in the areas related to quantum technologies, and in particular, quantum information and quantum computing. This group of QCQI in the Institute has a good mix of theoretical and experimental physicists. And they are working on areas related to quantum optics, quantum mechanics, quantum entanglement, NMR, optics, and so on. The government of India has also several large programs of which the institute faculty have an integral role in technology under the national mission of the government on quantum technologies and applications. And even in that program, which is yet to be rolled out, but is in its advanced stages, the faculty at IISER Mohali have played a very large and integral role. So given that background, I'm very sure that the colleagues of mine in the faculty at the Institute will play a very important role in the success of the present conference. And I take this opportunity once again to wish all of you the best in the proceedings that are to follow in the next 5 or 6 days. Thank you.
Thank you very much, Professor Gowrishankar, for the nice overview of IISER Mohali and the QCQI research activities. I now request my co-convener, Sandeep Goyal, to take over, chair the session, and introduce the speakers for this session. Over to you, Sandeep.
Thank you, Kavita. And I thank Professor Gowrishankar for inaugurating the conference. This is the second edition of Quantum Foundations Technology and Application. We have over 200 registered participants in this conference and over 60 expert talks, and which are distributed over next 6 days. Our first session of the conference starts with a blast. We have two speakers in this session, Professor Lewenstein and Professor Arun Pati. Our first speaker is Professor Lewenstein. Let me introduce Professor Lewenstein a bit here. Professor Lewenstein graduated from Warsaw University in 1978 and received PhD from SN in 1983 and habilitated in 1986 in Warsaw. He has held many positions over the years. Currently, he is an ICREA research professor at ICFO Spain. His research interests include quantum optics, quantum physics, quantum information, many-body physics, attosecond science, and statistical physics. He's also an acclaimed jazz writer. Today, he will be speaking on storage capacity and learning capabilities of a quantum neural network, and we can request him to give a talk on the jazz writing sometime in the future. So I'll request Professor Lewenstein to share his screen, and we start the, yes.
Okay. I'm going to do that now.
If you scroll, there is a screen share button.
Yeah, I have to open that.
Meanwhile, while we are setting up this, I request all the participants to please either, if you have a query, keep it till the end, to the end of the talk. We will have a 10 minutes question and answer sessions. And meanwhile, you can type your question in the chat box, or you can raise your hand and we will address your queries at the end of the talk. Professor Lewenstein.
Can you see it?
Yes, we can see it.
Okay, open it now. All right. So I start. Okay, so hello everybody. For me, it's good morning. For you, it's already nearly good afternoon. The talk that I will be giving in this conference is about quantum machine learning. And it will be very simple, very introductory. This is the first talk of the conference, so I want that the students can understand some ideas. It will be more about ideas than about new results. So the first transparency shows that all these agencies that give money for supporting of my group at ICFO, at the Institute of Photonic Sciences in Castelldefels in Spain, in Catalonia. The title, as I said, was said, is storage capacity of quantum neural networks. And I would like to dedicate this talk to the memory of Peter Vitek, who most probably died under the avalanche in India, in Himalaya. He was here devoted alpinist or Himalayist, if you wish, and one of the pioneers of quantum machine learning. So the group, because of all these grants, is very big, and it has many, so to say, Indian connection. Very many Indian colleagues have been in the group or running the group. At this moment, there is one postdoc, Bhattacharya, and one PhD, Mohit Bera. And we collaborate with many Indian colleagues. I mean, here you Mohit and so on. Let me tell you the outline of the talk. I will start with it will be very introductory. I will start with the introduction to classical neural networks. I will talk about learning concept, what is learning in this kind of everything classical so far, and then I will tell you something about the storage neural network. So I will define what I mean by quantum neural networks, and then give you the answers which come from our recent paper, but I will not go into details of proof. me or check it. I will make very short comments about Outlook. Classical neural networks, okay. First of all, let us talk for a moment about the real neurons that we have in our brains. So the real neuron, here you have a picture of the cell, which is called neuron. I mean, it has as a biological cell, it has a nucleus. Then there is this, there are these dendrites coming to nucleus, which will bring the information from other neurons to this one. Then when this guy is excited sufficiently, then it shoots an electrical signal which goes through its long axon to the end here, which are called synaptic terminals that connect to another neurons. This all, this picture even, I would say, is copied from the one and only Spanish Nobel Prize winner in sciences, Santiago Felipe Ramón y Cajal, who has more or less described the physiology of neurons in the end of the 19th, beginning of the 20th century. Santiago, I mean, funny thing about him is that as a child, he was transferred from one school to another because he had very anti-authoritarian attitude. So extreme example of this was that of his precociousness and rebelliousness character was that at the age of 11, he was imprisoned for destroying his neighbor's yard gate as a with a homemade cannon. There's some from the museum of Ramón y Cajal from Ayerbe in Navarra, where he was going to the. Okay, very early in the last century, people started to think that maybe one would like to make models, mathematical models of neurons in order to somehow mimic how the information processing occurs in our brain. Is impressed by the fact that the information processing in our brains occurs quite well, so one wanted to mimic it. One of the first these mathematical models was the so-called model of McCulloch-Pitts. Here you have the photo of guys who were actually, I remember, engineers. Now, the idea here is the following, that the neuron is something that gets inputs to this nucleus. So the inputs are here, I1, I2, IN. These inputs are weighted with some weights, which corresponds to the strength of this synaptic connections. And then the summarized input, so the sum of all these inputs, comes to the center of the neuron. And here it is analyzed. If it is bigger than a certain threshold, then the neuron reacts with the active signal. If it's smaller than the threshold, the neuron does not do anything. This was the mathematical model of McCulloch and Pitts. And this model was, in a sense, also analyzed very strongly in this kind of simplified even version by Frank Rosenblatt, who has called it perceptron. And this has stimulated a lot of excitement in the artificial intelligence, in the so to say, freshly born artificial intelligence community, that maybe this will solve all the problems of intelligence. So the perceptron is like McCulloch-Pitts neuron, except that here we take threshold to be 0 just to be. That was for a very long time, this perceptron was thought that it can solve a lot of problems with artificial intelligence, until came two people from MIT, Minsky and Marvin Lee Minsky and Seymour Albrecht Papert, who has shown that this simple perceptron is not useful for everything. In particular, it is able only to do this kind of linear classification or linear distinction between the inputs into two categories. So you can imagine that the inputs live in multidimensional vector space, and the perceptron is classifying them into, let's say, white and black. And then if the set of white can be separated from the black points by a hyperplane in the corresponding multidimensional vector space, then perceptron can do it. There is an algorithm to teach the perceptron to do it. If, however, the so to say configuration of these points which you are supposed to distinguish is more complicated, is separated by the nonlinear manifold like here, then the perceptron cannot do it. And this no-go theorem has in a sense killed the interest in perceptrons for very many years, because people were saying this machine is not even able to realize the simple logical function like the so-called extended OR. So it's a logical function which is one only if one of the entries is true, one of the entries is not true, but if both are false and both are true, is zero. So the things has changed in more or less in the beginning of the 80s, because the people came after this no-go theorem of Papert and Minsky and Papert. The artificial intelligence was mostly go into this direction of decision trees, of optimization, of taking decisions on each level, branching the information processing and things like that, until more or less the 80s, where came the era of neural networks, attractor neural network and feed-forward neural networks. I will only talk about attractor today. So attractor neural network is a dynamical network in which there are many neurons that are connected one with another and that undergo certain usually dissipative dynamics. The typical example here will be like that. I will take my neurons as just Ising spins, so plus minus one, you can think about it, or 0, 1 if you prefer. So the S here, Sj, is a jth neuron at the time t, with the which will be equal to plus minus 1. Now, this neurons at j are multiplied by the weight j, capital J, ij, which describe the signal coming from j to I, to the ith neuron. So the total summation here gives me a total signal coming to the neuron ith, and if it's bigger than the corresponding threshold, I put the neuron ith at the time t plus 1 to be equal to plus 1 or minus 1 if the signal was smaller. Neurons that can have 3 states, you can imagine with the neurons that have states that are continuous between minus 1 and 1, whatever. I mean, there are thousands of generalizations. The way of thinking about the attractor neural network is that this is a dissipative evolution in a kind of complicated landscape, like in the Himalaya mountains, okay? And the network, what it does, it essentially seeks the closest local, let's say, equilibrium state in a valley. This is, of course, not necessarily true, because this kind of dynamics is not necessarily described by the energy landscape. Does not have energy functional, but usually there are some Lyapunov functionals that play similar, or some kind of cost functions that tell you that dynamics really does something like that. You start from here and you go down to some kind of stationary state, which is the minimum. So indeed, stationary states in this kind of systems correspond to memorized patterns or correspond to what you have in the memory. So attractor neural network, it is pattern recognizer and associative memory in the sense that if you start close to a pattern that is in your memory, then you are attracted to it. Recognition here corresponds to attraction toward a certain stationary. Well, this has the big boost in understanding neural networks comes from the famous Hopfield model that was introduced in the beginning of the 1980s in the last century, which is exactly the same model with a very small restriction that the connections Jij are symmetric. So whatever jth neuron does to the ith neuron is the same as the ith neuron to the j. In this case, the whole evolution can be interpreted indeed in the term of the energy functional. So the Hamiltonian diffusion of energy is defined like by this formula. So it's an Ising model with interactions that corresponds to Jij's symmetric and with some external magnetic fields, which are Zeeman field, you can say, corresponding to this threshold. John Hopfield, who wrote the famous paper in 1982. Here you have this picture that I show of this Himalayan landscape in which you go down to closest valley in the process of dynamics of the Hopfield model is exactly correct. So it really looks, the dynamics looks for local minima of the energy. If you add the noise to the dynamics, or if you add some temperature to the dynamics, that it will seek for the minima of the free energy. But all the other statements that I made are still true. The attractor neural network is pattern recognizer. It's a content addressable memory or associative memory. Recognition is attraction toward a set. Now let's start thinking a little what is the storage capacity, which is the main subject of this lecture. So we want to store P patterns, memories of stationary state in the network. Let's start with the kind of fundamental problem in which the patterns are completely random. So they are given by sequences of plus minus ones that are this psi mu j I, where I enumerates the neuron and mu enumerates the pattern. All these guys are random independent variables with probability plus minus 1. With probability, sorry, 1/2 for plus and minus. Okay, so what we want to do in the dynamics is that if I put the mu pattern on the input, I should get the same pattern on the output. So I put it here, and this should happen for all patterns because I want to store all of them, and for all neurons, so for all eyes. It was again in the famous paper of Hopfield that he has realized that if the number of patterns is much smaller than the number of neurons, the storage is possible essentially without any errors or with exponentially small. In contrast, if the number of patterns that you want to store is proportional to the number of neurons, the storage is only possible if alpha is smaller than certain critical alpha. So it's really a phase transition. And above this critical alpha, the system behaves completely chaotic. Below, it stores the patterns with some small errors, but let's say reasonably small errors. How should I understand this effect? Well, it's very simple. If you remember your times when you were kids and you were playing in the sandbox and you were trying to, so imagine you have a sandbox of a finite size and you want to dig with a given spade a certain maximal number of holes in this sandbox. Well, if you put too many holes, then they will start to overlap and you will get simply a chaos. You will not have holes which would correspond to minima of this local energy, but rather you have something which is completely chaotic. So let's make first comment about what is the learning. The learning in these models is, of course, adapting connections, interactions, and threshold, adapting parameters of the of the system. So for instance, if I want to store this completely random patterns from mu equal 1 to p, one of the possible, so I want to achieve this, what I have to do, I have to modify these JIJs and maybe thresholds in order to get, sorry, P for thresholds and sometimes H for because of association with. I have to modify these parameters in order to achieve that if I put on the input the pattern mu, I get the pattern mu on the output. So how can it be done? So one thing is that I simply have prescription for the rules. So these are called for the couplings, JIJ. So this is called learning rules. So we want to store these p random patterns. One of the ways of doing it is by the so-called Hebbian rule. Hebb was another neuroscientist in the middle of, who invented this rule in the middle of the 20th century. So the rule is essentially that Jij are given by 1 over n number of neurons. This is for normalization, which is used for the distance of the thermodynamic limit, but it's not important at this stage. Product on projection operator of discrete configurations, summed over mu. Now, this means that if in the, it's +1 at j and +1 at I, then this configuration, this pair contributes with they are in support in they are if they j is positive and I is negative or vice versa, then the contribution to the Hebbian rule is negative, or if you wish, it is diminishing the signal, so it's inhibiting the excitation of the neuron. How can I understand the storage capacity in the network that with this kind of guys who are random independent, identically distributed variables with probability that psi j mu is ±1 with probability 1/2. One of the ways to looking at this equation, so I put spins here for a moment generally, and I as a kind of this the stationary state for a given configuration will be will be bigger than 0. So for these configurations, indeed, the configuration S will be stationary for this thing. But actually not bigger than 0. It should be bigger than this threshold. But let's take for a moment threshold equals 0, so we will be a little less technical. So then I can divide the signal that comes to the ith neuron into the contribution. Well, it has this form. There is no threshold. There is only this in the Hebbian rule. So now it has a sum over all patterns. And if I want to store the pattern number 1, let's divide it into a contribution from pattern number 1 and the rest. So the contribution from pattern number 1 is very simple, because that means I put in terms of S, I put psi 1j, and I take mu equal 1. So psi j1 is 1. So this is a very simple thing. And now if I multiply it by some, so this is the result, more or less. And there is the rest, the contribution from other patterns. So if I multiply the signal by xi, I get this formula. I get something of order 1 plus contribution of other patterns. P is smaller than 1. In practice, if P will be comparable to N, the noise will be comparable to 1 and therefore can compete with the signal, and therefore the storage cannot be much bigger than alpha times. So once more, the general properties of the learning are that we want plane that's distinguishing multidimensional vector space, this combination, so perceptron can recognize this. And then there exists a convergent infinite number of step perceptron learning algorithm. The same algorithm can be, or for the similar algorithm can be generalized actually for attractor neural networks for feed-forward, a famous error backpropagation algorithm. So the latter algorithm is sometimes to teach from example. But the things that I want to mention to you is the famous Gardner program, which was introduced by Elizabeth at the end of the 80s. And this is related to the space of interaction in neural network models. So the perceptrons that fulfill the tasks. So this is again integral over the J's. Delta, the constraint describing the sum of J squared is equal to N. And then the product for each pattern, I should have the situation that my signal multiplied by the output should be bigger than a certain, in principle should be bigger than 0, but she introduces some parameter kappa to have, which essentially controls the size of the the stability, let's say, of the relation. And then she calculates relative volume in the space of interaction. So it's a ratio between volume task to volume total. And if this relative volume is big, then fantastic. Then there is many machines, many perceptrons that fulfill the input-output relation that I want to realize. If, however, this relative volume shrinks to 0, then there is no chance to find a perceptron that will fulfill this relation. So that's a Gardner program in essence. It has been applied in the last 30 years to everything possible, and it's very successful in classical machine learning. Now let me go to the final part, which is the few sentences about quantum Gardner quantum machine learning and quantum version of Gardner's program. There is some history. Actually, I have written. I was obsessed by this problem for several years. So this was 26 years ago. Then I wrote this paper about the quantum perceptron when I analyzed the I mapped the I consider quantum neural networks in a form of simply unitary transformation of the density matrix of a given system, following that time the prescription of Seth Lloyd, how to make a quantum computer. One has input states of the computer without knowing results of computation. The system must transport inputs into outputs. This was done here by unitaries, and then one has to be able to perform measurements so that we extract results of computation. It was a very primitive paper, but anyway, as I said, I was obsessed by this problem. There are much more interesting papers about quantum associative memory by Dan Ventura, Antonio Martinez, and also by Seth Lloyd group, in which they actually discover what I'm going to discover now what I'm going to present in a more general sense, that the storage capacity of quantum neural networks defined in certain sense, like analogy of the Hopfield model, can be exponentially large in comparison to the storage capacity of. So the paper that I'm going to mention now in the last 3 minutes is storage capacity of quantum neural networks. It is on the archives, but I have I didn't put the number. You can find it easily. So the idea here is to the question that we ask is, we define in a certain way what the quantum neural network are, and we ask how many stationary states this attractor quantum neural networks can have. We answered this question by first of all showing that maximal number of states is actually equal to the dimension of the Hilbert space on which the machine is working, and we also apply the Gardner properties. So the first thing is that how do we define attractor neural networks? Well, we define them by CPTV maps, completely positive trace preserving. You have a density matrix on the input, you have a density matrix on the output. The maps are linear. The maps, of course, conserves Hermitian conjugation. The maps are positive, so when positive operators are positive, and the maps are completely positive. So if you extend the map to arbitrary bigger Hilbert space, on this extension, the map is also positive. So with positive inputs, get something. And the trace preserving condition means that the trace of the lambda of rho is equal to the trace of. So you can think about this attractive neural networks as something that schematically transforms states into and attracts them to a stationary state. As I said, this attractor neural networks defined in the way with the CPT maps can be interpreted. On one hand side, I can just say that this is transformation from initial rho to a rho at finite time, and then I should iterate it to see how the dynamics goes. So this is the picture that is here. But I also can interpret it as a map from initial state to a state immediately at t equal infinity. And I also can interpret it as infinitesimal dynamics, the transformation of the state to a state at time all increment. But in any case, stationary states correspond here to stationary patterns. So my question that I want to ask, how many stationary states a CPT map can have? Being, of course, not trivial, because I can take a map which is identity map and then all states are stationary state, but that's trivial. Doesn't distinguish like that. So one theorem that we proved in this paper is that for n qubits neurons, a quantum attractor neural network can store up to 2 n patterns. So this result was mentioned in the previous papers that I cited, but here we really construct a CPT map. We construct the whole family of parameterized all the maps that has this property that they have for acting on the space of n qubits of dimension 2 to the n, it can store p equal to the n. Roughly speaking, the proof is like that, that we restrict ourselves projectors on the vectors in Hilbert space of pure states. we first canonically transform these independent vectors into orthonormal basis, and then the desired map then acts on the projectors on orthonormal basis, and then we simplify it, or we prove how its construction using the famous Yamakowski-Choi Sudarshan relation between the maps and the operators acting in the doubly bigger space. So the map that is that has this property that it stores 2 to the n states, we can prove generally that it's a kind of generalized decoherence map. So it's a map which in this computational basis has this properties that acting on the general state in this basis, it multiplies the off diagonal, if multiplies the diagonal elements by 1 and multiplies the off diagonal elements by something which is smaller than 1, essentially. So it's like decoherence in the general state. But we proved that this is the most general form. There is no but state volume of quantum attractor neural networks storing P patterns, and we proved that if P is smaller, it decreases with P as for the storage of pure state, it decreases like exponentially with P squared divided by this number n squared minus n2, which is more or less the dimension of the manifold of CPT maps. So you see, if P is much smaller than n, this decreases, but this decrease is much more smaller than, but the decrease is very small, very slowly, because P is much smaller than n, and you have here n to the 4. And this, I mentioned, this volume shrinks to 0. On the other hand, for P bigger than 2 to the n, which can be proven as in the way that I discussed a minute ago. But otherwise, it's a nice estimate that it shows that in principle, you have for small number of stationary, you should be able to teach the quantum neural network to realize the tasks you want. I mean, I can show you some of how the relative volumes look like. All these results are based on the all the theory of people who were calculating volumes of compact manifolds of unitary groups and other sets. So in particular, the mentioned Sudarshan also wrote several very beautiful papers on this subject. We use particularly the results of the paper by Stanisław Szarek, Karol Żyżkowski, and Elizabeth Werner, and then we get this kind of estimates for the volume of all CPT maps and the volume those CPT maps that fulfill certain m number of constraints corresponding to the stationary states. During the so this more or less looks like that the volume, of course, of the maps that have n stationary state is smaller than the volume of all the CPT maps, and how smaller it is the question. That let me give you an outlook. The outlook is how to try to realize this thing in experiments, and we are talking with several experimental groups that have to their disposal the dissipative dynamics, and maybe something can be done. Even very much for your attention.
Thank you, Professor Lewenstein. This was a wonderful talk, and I hope everyone enjoyed here. There are a couple of questions, and I will just call them one by one, and they will ask questions. First one is Sarang Bhosle. Sarang, please switch on your mic and ask the question.
Hello, sir. Am I audible?
Yes, you're audible.
Sir, I wanted to ask that in the previous field model, you described about adjusting JIs and HJs. So I didn't get what they do signify. like in mathematical terms also and in physical terms also? What do they basically signify?
What do the JIJs signify?
Yeah, yeah.
Okay, so if you think about the analogy to the neurosciences, the JIJ or JIJ describes the strength of the influence of the neuron J on neuron I. So the neurons in the brain are connected, and the strength of this connection tells you how strongly a given neuron influences the other neuron. And they are numbers, they can be quantified, okay? So this is in the analogy with neurosciences. In the simple Hopfield model, where you have interpretation in terms of energies, these are just couplings between the spin. The Hamiltonian is the Ising spin Hamiltonian. So it's spin I interacts with spin J. The interaction energy is Jij. It can be positive or negative, like in spin glasses, because the neuron J can influence neuron I to activate it or to inhibit it. Okay, so these are, you can think about it like that. It's very similar, actually. The storage of patterns which are random in coupled neural networks is really very similar to the model becomes very similar to the spin glass model, because it has JIJs that can be positive, negative, and are random. Okay, is this clear? So JIJ in the Hopfield model is energy of interaction of spin I and spin J.
Okay, sir. Thank you so much.
And it's symmetric because the energy of interaction of I and J is the same as J and I.
Yes. Yes.
In the case when it's asymmetric, it doesn't have such a simple interpretation, but you can think about some Lyapunov functions, which it's not energy, but it's something more general. But it's only maybe mathematical generalization, but not so important.
So next question is from Vasudev Mittal. Vasudev, you can switch on your mic.
Good afternoon, sir.
Good afternoon.
Good afternoon.
It's afternoon.
Well, good morning for me. Sorry.
Sorry, good morning. In the last but one slide, you talked about that operator gamma. Like, what is that function? If you can please specify that.
I have to look what I did. No. This is just the formulas of the, in the last slide, maybe I should show it because otherwise. Gamma is gamma function, is a special function.
Okay, so it's just a simple
Okay, so in the last slide, I gave you the analytic formulas for the volume of CPT maps and of the volume of those CPT maps that fulfill the task that we wanted to fulfill. And this can be expressed in special functions, and in particular, the gamma function plays a role here, which is just a standard gamma function. So for the arguments that are typically here integer, this is nothing more but the argument factorial plus argument plus 1 factorial or minus 1 factorial. But these are just a standard thing. Yes. So it's not an operator, it's just a function. It's just a number given by the gamma function.
Thank you, sir.
Okay, so next question is from Manavendranath Bera.
Hi, Manav. Hi, Maciej. So thank you for the talk, though I still have to understand the details, technical details. So I have a couple of questions and they're interconnected in some sense. So whenever you talk about the storage capacity and so, it means that I give you a map and you look for the volume of states which remain unchanged through that, right? This is what you define, no?
No, I look at the volume of the machine, the maps that have this property that they have given set of stationary state as stationary set. Which given means, I mean, I take it random because I want to have result independent actually on the character of the stationary state.
So that means you have state which you define to be like having all the details of the pattern, and then you look at the set of states which leave the states remain intact. No, Maciej, if I understand it correctly. So my question
Once
is now.
more, I have a set of all maps.
Yes.
And now I ask myself, so every CPTP map has one stationary state, at least, because the trace is preserved. But anyway, so I'm asking, let's look for the maps that have stationary states given by projector on zero and projector on 1. How many states of this sort I have? And I do it by calculating volume in the space of CPT maps full and volume of the space of those CPT maps that have stationary state 0, projector on 0 and projector on 1. So the second volume is smaller, I calculate the ratio, and this is what I analyze, okay? So in principle, I take not 0 and 1, but I take P of these states, but all of them will be, mostly I concentrate here on the pure states, so on projector on some, let's say, random vectors, and this is what I'm trying to do, random vectors, so if you wish on random orthonormal, how do you call it, basis of M things.
So the second question is
Stiefel manifold, random Stiefel manifold. This is what I'm trying to do. I have random Stiefel manifold of the inputs, and I want these inputs to be stationary states. And my question is, how many CPT maps fulfill this?
Okay, Maciej. So if I ask now, so you have like 2 to the power n, no, the storage capacity, and so it scales like this.
One can prove, yes, that it's 2 to the n.
But if I just restrict myself to the classical world or classical formalism, so how I compare it? Is there some way to compare?
This is what I was trying to explain you at the beginning. If I have this neural networks like defined in the Hopf field, then for n neurons, in the storage is of the order of n.
Okay, it's a polynomial. Okay.
So it's polynomial in the end.
Okay. Maciej, second question.
Because you have to compare number of neurons with number of qubits. This is, I think, the fair comparison. So that's why I'm saying classically you have polynomial, and here you have, although of course you pay the price, because as you know, linear maps has the property that if something is a stationary state and something other is a stationary state, then the mixture is also a stationary state.
Correct.
Which is something that, for instance, classical neural networks to some extent avoid. Of course, they have also this kind of superficial mixture state to be a stationary, but typically each of the stationary state in classical case has a nicely defined attractor region. Okay, so it's really a local minimum, but if you are close to it, you go to it. You don't go to any mixture of two of them. So this is something that you pay by the definition that your quantum neural networks is a linear map, because the neural network models of Hopf type are essentially nonlinear.
Okay, Maciej. So that more or less clear, and just a vague comment, because I just see some similarities maybe there. So let's say I have a quantum map and I repeatedly apply. So we know that almost all CPTP map, they bring a state to a fixed point or something, no?
Yes.
So is there some something, because every time you also repeat your operation, no?
Yes. So here is the same story, but as I told you, any CPT map has at least one stationary state, which is due to the fact that it preserves the trace. But it can have more stationary states, and this is the question that we are answering. How much more? How many more? Okay?
Okay. Now I think I see it better. Thank you so much, Maciej. Thank you so much.
If there are no more questions, we will thank Professor Lewenstein for his wonderful talk. And we move on to the next, our next speaker, Professor Arun Pati. I think, Arun is here.
I'm here, yeah.
Hi, Arun. Yes, hi. So let me introduce our next speaker, Professor Arun Pati. He's a professor in Quantum Information and Quantum Computing Group at Harishchandra Research Institute, Allahabad. Over the years, he has held positions in BARC and IOP Bhubaneswar. He was a visiting scientist at the University of Wales, UK. His research areas include all aspects of quantum computation and quantum information, the theory of geometric phases, and foundations of quantum mechanics. And today he will talk about non-commutativity, superposition, and coherence. So I'll request Professor Arun Pati to share the screen. And
okay, thanks, Sandeep. So let me start sharing my slide. Just a minute. So can you see my slide?
not yet.
Can you see now?
Yes, yes, we can see it now.
Is it full screen or?
It's not full screen yet. What is this? What is in the page display? Will it not give you the full screen?
Let me share the PPT file. This is PDF file. Can you see my slide now?
It's still not full screen. We can see your screen, but like we see the details around the file also.
Can you see now?
We can see your slides, but again, not full screen.
Arun, I think it's okay. We can continue.
Can you see now?
Yes, now it's full screen.
Okay, okay, good. Okay, so thanks the organizers for inviting me to this wonderful conference. So today I'm going to talk about non-commutativity, superposition, and coherence. So yeah, so quantum theory has been there for more than 100 years, but still it continues to surprise everyone. And at the heart of quantum theory, we have so-called this quantum superposition, which tells you that if you have a quantum system in two possible states like psi1 and psi2, then it is also possible for you to have a state which is a linear combination of psi1 and psi2. And this is possible because you have so-called quantum superposition between two or more possible states. And if you recall our wave particle duality that we learned in our graduate days, we know that in quantum world, every entity behaves not only like a particle, they also behave like wave. Okay, so this cartoon is a depiction of this wave particle duality. For example, a photon does not know where I am, or what is my momentum, or where I am, look at that, and so on. So this wave particle duality is something which has been there for more than 90 years, and still we do not understand the complete picture about this quantum entity. And soon after this particle duality was proposed by de Broglie, people did actually experiment with Young's double slit setup. And as all of you know, if you have this double slit setup and you send particles like electron or photon one by one, and you wait long enough, you do see an interference pattern. And this is a phenomena which is impossible, absolutely impossible to explain in any classical way, and which is in it the heart of quantum mechanics. In reality, it contains the only mystery. And this mystery still continues, as I will try to highlight during my talk. And interference, to explain this interference, what you do is you say that you associate two amplitudes, psi1 and psi2, for the particle going through both the slit, and you say that the probability of finding the particle at any point on the screen is essentially mod square of these two amplitudes, sum of these amplitudes, and that's how you see the interference. And as I said, the mystery continues because still we don't yet know in reality what a quantum entity is. Is it really a particle, or is it really a wave, or is it really both particle and wave? Because recently there is a paper which claimed that a quantum entity is neither a wave nor a particle. It may be possible that the quantum entity is something else, and we associate, or we describe using this wave and particle duality picture, which is only an approximate version of actual what it may be the quantum entity is. And just to tell you how curious this wave particle duality is, when I first time learned this wave particle duality in my, I thought maybe something is wrong with quantum mechanics, and maybe something is deeper than this wave particle duality, and that's how so this quantum superposition that actually comes due to this non-commutative nature of two or more observables, and that plays a major role in quantum theory. So if you ask this question, how does one create quantum superposition? The answer is easy to see, because if you prepare your quantum system initially in one of the eigenstate of A, like this is initial state, and that could be in one of the eigenstate of some observable A, and then you apply unitary operator, which is generated by some observable B, and A and this B, they don't have to commute. If that is so, then you will create a quantum state which is in a linear superposition of all possible eigenstates of A. So at time t0, system was initially in one of the eigenstate. At later time t, you create a state which is a linear superposition of all possible eigenstates of A. And just for students, this is very illustrative to see this example. So you prepare initially your qubit in state 0, and that could be in one of the eigenstate of this, say, sigma z, and you apply unitary, which is generated by x or z, sorry, x or y, which don't commute with z. Okay, so for example, you choose u to be exponential with theta is real number, real parameter, and if you do this, you can create a state which looks like alpha 0 plus beta 1. Okay, so starting from an initial state 0, which is one of the eigenstates of sigma z, you create actually a arbitrary quantum state, which is a combination of 0 and 1. So non-commuting nature of A and B create a state which is a superposition of eigenstate of this observable A, which you can express like this. And this is true not only for 2 dimension, in any dimension you can create such a quantum superposition. And now we know from coherent superposition of different amplitudes, and this notion of coherence is actually a basis dependent notion, because if you try to see the coherence in its original basis, in its own basis, you will not see any interference. It is quite surprising that even though quantum superposition, this particle duality, quantum interference, everything is there for more than 90 years or more, was not really quantified in a rigorous manner until 2014, when this Plenio group tried to formalize more rigorously using so-called resource theory of coherence. For example, if you look at the classic textbook by Kohentanuji, you do see a definition of coherence. So in that book, you will find that populations and of diagonal elements, they represent coherence. But there is no quantification of how much coherence is there in a given quantum state. So for example, if you want to really quantify, ask this question, how much coherence is there in the density matrix rho or a quantum state psi, there is no answer actually. So this was the thing as I mentioned. So Plenio group, they did this in 2014, which tried to formally quantify this coherence of a quantum state with respect to a given basis. So essentially what they do is that if will have zero coherence, and they will define some free operations which will not create any quantum coherence. So essentially free states are those states which are diagonal in that given basis, and free operations are those which are also called incoherent operations, which will not create any coherence. And they will also map incoherent state to incoherent state. And every Krauss element individually will map incoherent state to incoherent states. And over the last couple of years, there have been tremendous progress in trying to develop different definitions, different formulations of quantum coherence, and there are many variety of incoherent operations has been introduced in literature, but I will not go into all those details. So I will stick to this definition of this set of conditions that was laid down in 2014, which you would need to define a proper measure of coherence. So first condition is that for any incoherent state sigma, you will say that the coherence measure should be 0, because that's what you want ideally. And for any other state, you would say that that measure should be finite, that is, should be non-zero. And that should satisfy this so-called weak monotonicity under incoherent operation. That is, if you apply channel, incoherent channel lambda on the quantum state rho, you should not be able to increase the coherence. And there is the strong monotonicity under the incoherent quantum channel. That is, if you apply quantum channel with this Krauss element Ki, and if you have this selective quantum state sigma I, then on an average, this quantum coherence again should not increase. And finally, they impose this condition so-called convexity. This is desired, but not necessary. That is, if you have this density matrix, which is a mixture of all this rho I, then under mixing, the C of rho should satisfy this. And with this suitable features of this coherence measure, they identified a couple of several measures of coherence. So as I said, you have to fix a suitable basis. So coherence method begins with identification of a preferred orthogonal basis, and the probabilistic mixture of orthogonal basis states, you call that as a incoherent state, and quantum states that don't belong to class of incoherent state will capture some non-zero coherence. And this coherence is essentially could be quantified in several ways, and one of the way to do is to identify how much you accumulate, how much non-zeroness you accumulate in off-diagonal terms of the quantum density matrix expressed in that particular preferred basis. Okay. So over a couple of years, I mean, as I said, several measures have been defined, but these two measures are quite quite useful and very handy and user friendly, because you can do many things using these two measures. One is called L1 norm of coherence, and the other one is so-called relative entropy of coherence. And this L1 norm of coherence is essentially sum of modulus of this off-diagonal elements rho ij in a given basis I. And the relative entropy of coherence is essentially the entropy difference of the diagonal part and the original density matrix. So essentially what you do is you write your density matrix in that particular basis, and you delete all the diagonal elements and look at this density matrix in its diagonal form and find the von Neumann entropy, and that is S of rho d. And S of rho is the original von Neumann entropy of the density matrix, and that difference is essentially the C of rho, CR of rho. Okay, and the first operational meaning of this L1 norm of coherence came in 2015, and where we tried to prove that if this coherence is indeed capturing this wave nature of quantum entity, we should be able to prove some kind of duality between coherence and path information, and that's what we did with Manav and Qureshi and his student in 2015, and we did rigorously prove that indeed this L1 norm of coherence and path information that satisfy a duality relation, and this Englet famous duality actually turns out to be a special case of this duality relation, or actually equivalent to this. And we also tried to figure out, try to give an operational meaning to this relative entropy of coherence by proving that how much thermodynamic cost is involved when you want to erase this coherence. Okay, so we try to prove that minimum entropy that you need to inject into the quantum system to make that an incoherent operation for an incoherent state is actually equal to this CR, which is defined here. Okay, so this was again done by some of our students, but like Uttam and Manav was here as the postdoc, and Abhijit, and that was kind of quite satisfying. And as we know, now this quantum coherence is depends on choice of basis. That is, if you choose a basis I and you find that system has some coherence, and if you choose say another basis mu, you may not find any coherence. For example, if you write the density matrix in its own eigenbasis, obviously in that basis you will find the density matrix will have zero coherence. And for any density matrix, for any quantum system, there are infinite number of bases you can choose. That means you can define infinite number of different coherence for a given quantum state. So if coherence captures wave aspect, then for a quantum entity, there is not just one wave. There are actually infinite variety of waves, which I call myriad of waves you can associate to a quantum entity. So if I carry over this wave particle duality to each of these waves, that means for each of these waves, I should be able to associate a particle. That means there should be an actually infinite variety of particles that I can associate to a given quantum entity. That means I should be able to equally, associate a myriad of particles for a given quantum entity. So you see, the wave particle duality that we are taught at your textbook level is kind of really a misnomer, because as you see now, quantum theory actually tells you that there are not just one wave, not just one particle. There are infinite number of variety of waves you can associate. There are infinite number of variety of particles you can associate to a quantum entity. So thinking along this line, we try to quantify what do we mean by a particle. And quite strangely, we found that this is the kind of thing that we understand in classical world, that this is a classical particle like football or or any classical entity, is not really true for a quantum entity. Okay, the quantum particles are completely different than these classical particles, and that motivated us to define, not really define, I mean to propose a kind of resource theory of particle, and we try to quantify the particle aspect of quantum system in this article. So it's still not clear, I mean, what do we mean by actual particle? So so maybe it's still an open question. So okay, so that is a bit of philosophical. Let me try to come back to something concrete. So what we tried to prove in subsequent years was we tried to prove something called uncertainty relations for quantum coherence, because if we say that coherence is a basis dependent notion, that means I choose a basis I see some coherence. I choose another basis, I don't see any coherence. I choose another basis, I see a different amount of coherence. Okay, so if this coherence depends on reference basis, can you prove some kind of trade-off, some kind of relation between different kind of coherence between different non-commuting bases? Okay, so with that motivation, we try to prove that if you have a quantum state rho, and if you choose a basis I, and if you choose another basis A, where A and I are essentially incompatible, then we found that they satisfy this, which is actually kind of equivalent to so-called this entropic uncertainty relation that we know. Okay, so you see this coherence measure and this trade-off relation between coherence in different bases is giving a new meaning to entropic uncertainty relation that we all know, because that essentially tells you that coherence in different bases are not really arbitrarily, they can take arbitrary value. They actually are restricted by this this quantity C, which is a kind of incompatibility measure between I and J. Okay. So this was done by our group in 2016, and around same time we tried to explore whether this coherence is also useful in quantum computation. We do know, I mean, quantum superposition is actually that is key feature in all quantum algorithm. That's what is a resource when you think of a quantum computation or basic parallelism. So what we try to do is we try to figure out that in quantum search algorithm, actually coherence and the success probability, they are actually connected, and they're intimately related by this equation. So the success probability of quantum search is connected to quantum coherence in this fashion. So I'll not go again into detail, just try to highlight that indeed there is a connection here. So let me come to something that was done very recently by one of our students and with Ujjwal Sen in our group. So as I started, my slides, my talk, I try to motivate by saying that quantum coherence actually comes, because of non-commutativity nature of two or more observables. Okay, so if that is so, can we somehow connect this non-commutativity to quantum coherence in a more, more tangible, more feasible way, which will give a direct, connection to quantum coherence. Okay, that we started to think about this question, and actually we found out very interesting, very simple, very cute relation between coherence and this so-called non-commutativity. Okay, so what to do? You choose a basis I, and you want to define coherence in that basis, and you have a density matrix rho. Write that density matrix in that basis, and split that into two parts, diagonal and off diagonal, and you have some observable A. You write this observable in that basis I, and again split into two parts, diagonal and off diagonal. That is very easy. And what you can prove, you can check yourself is that trace of row a diagonal is essentially trace of row diagonal A. Okay, and what we try to prove is that this L1 norm of coherence is bounded by the commutator of A and A diagonal. Why this is non-zero? Because you see that we define this A, which is not going to commute with the observable whose eigenbasis is I. Okay, so this AT is something which will have a spectral decomposition in basis I, and we choose that basis. Sorry, we choose the observable A, which is not going to commute with I. So A and AD, they don't commute. And we tried, we could prove very neatly that this L1 norm of coherence is actually bounded by lower bounded by half of this average of this commutator. That means you choose any damn observable, up to you. You can choose anything you want. And if you could have a setup where you can measure this commutativity of A and its diagonal part, that will give at least a lower bound to the density matrix, sorry, to the coherence of the quantum state. So this gives several. I'm not going to prove here, but I'll just try to tell you the implication of this simple relation. So you could actually estimate quantum coherence from this non-commutativity. So this relation tells you a new bound that connects quantum coherence of an arbitrary quantum state. It could be pure or mixed in quantum system of arbitrary dimension, and the incompatibility measure of any observable and its diagonal part. Along with being potentially of fundamental use, it also provides a ready estimate because it gives a precise lower bound on the quantum coherence of an arbitrary quantum state without resource to quantum state tomography. As you know, if you want to measure this quantum coherence, typically you have to resort to so-called quantum state tomography. You do a state tomography, you find out all the elements of the density matrix. From that, you compute your off-diagonal elements, and from there you calculate, this CL1 and L1 norm of coherence. But without doing all those, you can actually estimate a non-zero value of quantum coherence if you can measure this non-commutativity. As a byproduct, it provides a direct method of creating witness for quantum coherence, which is unrelated to the existing witness operator. So if you are interested, you can look at this paper by Tanaya and myself and Ujjwal. So towards last part of my talk, I will tell you something about quantum coherence and how do they behave when you send a quantum state through a noisy channel. So when you send a quantum system through a noisy channel, or it could be a CPTP map, it could be a measurement channel, it could be anything. We know that it will undergo a decoherence, it will undergo a disturbance, and so on. Okay. So what happens to quantum coherence under such scenario? Okay, that is the kind of thing that we would like to answer in this part of my talk. Okay. So when a quantum system undergoes a measurement or a noisy map, as I said, we subject the system to disturbance. So measurement process not only disturbs the state, but also leads to loss of coherence. Essentially, we lose this off-diagonal element of your density matrix. And if there is no disturbance, system will not lose any coherence and it will retain all its original coherence. So it is natural to ask if there is a trade-off between disturbance to the state and to its coherence. Okay. So disturbance is an irreversible change that you cause to a quantum system, and we could describe that using a completely positive trace preserving operation, and it should satisfy certain reasonable condition that is this disturbance measure should be a function of initial state and the CPTP map only, and it should be null. The CPTP map is invertible in the initial state, because in that case you could change the disturbance that you have got the system, and it should be monotonically non-decreasing under successive operations of the noisy map. And finally, it should be continuous for maps and initial state which do not differ too much. Okay, so if you look at several papers in the literature, you will find a variety of definitions based on fidelity and Buress distance and so on. But they don't satisfy all the requirements. For example, they fail to satisfy so-called irreversibility condition. Like for example, if you use the fidelity-based measure of the disturbance, then that is non-zero even for unitary transmotion, which is not a desirable, definition. So, all the definitions based on this kind of thing can be null for non-invertible map, and they are not monotonically non-decreasing under CPTP map if you apply repeatedly. So therefore, they fail to satisfy condition 2 and 3. Okay. So interestingly, McConaughey defined this definition. I mean, he introduced the definition, which is very appealing, in 2007. So that looks like this. So you have a quantum state rho, and you send that state through some channel, and define the disturbance to be S of rho minus IC of rho, where IC is essentially the coherent information of the quantum state under the channel E. So coherent information, if you recall, it is essentially the state, the entropy of the state apply the channel minus the entropy of the joint state along with the reference system which you use to purify the state rho. So psi is essentially the purification of this rho that you are using to describe your system. Okay. And we know that this coherent information is essentially very interesting quantity, because that tells you that how much distant quantum information you are sending through a noisy channel, and it was known to be a useful quantity because that satisfies this feature that it is non-increasing under successive application of CPTP map, and hence that will get translated to this definition D of rho, and that satisfies this equality. I mean this bound. So what we try to prove is that the trade-off between amount of coherence and disturbance caused to a quantum system under noisy channel. And to prove that, you should consider density matrix rho and you purify to psi of SR, where R is your reference system that you use to purify that system rho. So what we try to prove is that twice C of rho plus disturbance is bounded by this. And if your channel is a measurement channel, then you can prove infinite ideal version of this trade-off, which looks like this. And if you think of a bipartite quantum system, you can ask similar question that what will happen to not only coherence, you can ask what will happen like discord and so on. So if you ask that question, so you can show that indeed you can prove an interesting trade-off between all these quantities. So for pure bipartite state, what is known is that there is complementarity between this relative entropy of coherence and bipartite entanglement, which is given by this. Okay, so amount of coherence in system rho A and entanglement that is shared by A and B bounded by this. This just follows from the definition of this. Okay, and what we do is we prove a complementarity between coherence, relative entropy of coherence. Relative entropy of entanglement and disturbance caused by the measurement or a CPTP channel acting on a bipartite quantum state. So what you do is you take a state rho AB, again you purify to psi ABR, and then if you use this relative entropy of entanglement for rho AB, you can prove very interesting relation. That is, for that you have to define disturbance for the bipartite state, which you can do like this by following similar spirit. You take the state rho AB, you define this coherent information for rho AB by again purifying to psi of ABR. So S of E of rho AB plus, this quantity is actually this minus this, and that's how this looks like disturbance. And to define the coherence, what you do is you take the rho AB and define the coherence in the basis I and mu. Okay, and then you can define S of rho diagonal minus S of rho AB even for bipartite state, and then you can show that the coherence and entanglement and disturbance satisfy relation which looks like this. Okay, C of rho and E of rho disturbance satisfy this quantity. Okay, so what this relations are telling is that capture this intuition that coherence, entanglement, quantum discord. Oh, I did not tell about discord, but if you have a density matrix which is separable, you can also prove that C of rho AB plus discord plus disturbance also satisfy something like this. Okay. So what you see here is that this coherence, entanglement, or quantum discord, they satisfy a trade-off with disturbance caused by quantum system. Caused by CPTP map acting on a quantum system. Okay. And these results will have interesting applications where we want to send singular composite quantum system on the noisy channel. As you know, whenever we send quantum system to the noisy channel, we tend to lose either coherence or entanglement or in quantum correlations. So the lesson we learn here is that if you wish to maintain coherence or entanglement or quantum correlation or even both, we need to send quantum state through a channel that does not disturb the system to a greater extent. Okay, and it will be interesting to see if other measure of coherence and entanglement actually respect the complementary kind of relation that we have proved here using so-called relative entropy of coherence. Okay. So with that, I am almost end of my talk. So let me try to summarize what I said. So I tried to motivate by saying that non-commuting observables actually play a very important role in creating coherence. Because that's what creates quantum superposition, and whenever you have superposition of two or more basis states, then you will see that in that basis you will have a non-zero coherence. And what we try to prove is that you take any dim observable A and you find out the non-commutativity between A and its diagonal part, and the average of the commutator of that observable A and the incoherent part actually gives a lower bound for the quantum coherence for any quantum state. It could be pure, it could be mixed, it could be anything you can think of. And towards last part of the talk, I tried to tell you that whenever you send a quantum system to the noisy channel, how do you trade off your resource like coherence or entanglement or quantum correlation? So we actually proved that coherence and this quantum resource like entanglement, they satisfy very interesting relation with disturbance. And yeah, so I mean, this tells you that your precious resource, you have to be careful when you try to send to the channel. So okay, so with that I want to end. So thanks for your attention.
Thank you, Professor Pati. And here we have hand raised. So Manav wants to ask a question. Manav?
Thank you, Arunda, for this nice talk. So I'm just, I think I missed this point. So whenever you talk about this disturbance, so of course you restrict some class of operation that have something to do with the reference basis, or like any arbitrary.
No. These definitions for disturbance could be any stability map. So you don't have to restrict to only I mean, they don't have to depend on the basis that you are choosing to define your coherence.
And so that means what you are looking at is that you look at the coherence before the operation and after the operation, and then so it's like a change in coherence and as well as the disturbance introduced, which because coherence is reference dependent,
yeah,
no? Because
so we did not look at change in coherence. We looked at the following situation, that you have coherence of the system in some basis, okay, and of course, I mean, we try to lose coherence. So we try to see how much the original coherence is getting, destroyed or getting traded off with disturbance. So the original coherence and disturbance, they satisfy this bound. Okay, so.
But there are CPTP maps that can introduce coherence as well, right? Because you don't restrict them to be incoherent operation.
Yeah, that can happen. Yeah, right.
Then if you say they are complementary, so that means ideally so you have to purify your system in that sense if you measure your disturbance in terms of entropy.
Yeah. Of course, that purification is there in definition, right? When you define the disturbance, we define disturbance as the entropy of the system minus the coherent information, and coherent information involves the purification.
Okay, makes sense. Okay, thank you very much. Thank you.
Gaurav?
Hi, Dr. Pati. Can you hear me?
Hi.
Yeah. So I have a similar question like that of Manav's. So as we define the coherence using a particular basis, so I just had a little confusion in understanding this trade-off between disturbance and coherence. So let's say I have a T state and I apply a CPTP map that transforms this T state into, say, the plus state. Now, if we look at both these states in the computational basis, then we see that, of course, the coherence is basically increased from going from T state to the plus state. So in this case, I do not understand how is there a trade-off between disturbance and this coherence.
So this disturbance and coherence, they satisfy this twice log D. Okay. So
right.
Yeah, so disturbance is anyway bounded by 2 log D. So this is so this is not that see, our relation is not telling you how much coherence you are creating after applying the channel. It's only telling you that how much coherence you are there initially and how much disturbance you are causing to system. Okay, because system is getting disturbed by the channel, and the disturbance system is doing something. Okay, losing something. So it may create coherence, it may destroy coherence, but that is. I mean, we're not claiming that there is some contradiction. You see, so in your example, initial coherence is 0, and our inequality is still satisfied, okay? Because disturbance is bounded by twice log d. It's okay. No issue about that, okay?
Okay.
I mean, what you are asking is a different question. So you have to put a different relation to capture what you are trying to say, okay?
No, I'm not able to understand how you're seeing it as a trade-off, because in one sense, when you're saying that disturbance is we are looking into disturbance as a CPTP
No,
map.
what did you say? You said that you take a system and you define you choose a basis in which initial coherence is 0, and then you are saying,
No. I'm saying that let's say I take a T state. So T state means I have some coherence initially present in the computational basis, right? Then I apply a CPTP map that converts this T state to the plus state. Now, plus state is the maximally coherent state. So we see that we have an increase of coherence, and we are applying disturbance using a CPTP map. So I do not see where the trade-off is coming from. Like, what do you mean by a trade-off here?
No. So initially a system has coherence or no coherence? What is your
There is some coherence. There is some coherence in the system.
So whatever coherence was there, that coherence will get traded off with disturbance. But you are saying coherence will be created. That aspect is not captured by this relation. See, that is two different relation. That's what I'm trying to say.
Okay.
So this is, I mean, there is no issue. I mean, what you're saying is perfectly fine. But to capture your scenario, we have to prove or you have to figure out a new relation which will tell me, okay, initial coherence, final coherence, and disturbance, or something. You know, you have to figure out that we're not done. Okay. So.
Okay.
Yeah. So there is another question from Inderjeet.
Yes.
So you may ask your question. I think there's some technical problem. Let me repeat his question. He typed that question. The question is how a coherence monotone differs from a coherence measure.
Yeah, essentially they're saying, I mean, when you define this coherence measure, we lay down some condition, and those conditions satisfy this monotonicity or weak monotonicity. So coherence monotone are essentially coherence measures.
So next is Sarang. Sarang, you can ask the question.
Hello, sir. Am I audible?
Yeah.
Yes, sir. So this may be a very basic question, but I didn't understand this. That why is the coherence the basis dependent phenomena? I mean, what exactly is the reason, and where could I read it more about?
Yeah. So when you take a quantum state, okay. Suppose you prepare a system in state say 0. Okay, take a qubit and you prepare a system in state 0 or 1. Okay. So in that state, if you do an interference, you will not see any interference pattern. Okay. So in its own basis, you will not see any effect of interference. But if you choose a different basis, like you choose plus or minus, you will see some interference effect. Okay. So essentially, that is the reason why we don't see. Telling differently, if I look at the quantum state in its own basis, it is like classical state. Okay. So classical state don't display any proposition or interference or anything. Okay? So that is a different way of looking at this scenario. That why we don't see interference in its own basis.
Okay, sir. Okay, sir. Thank you.
Yeah.
Manav, you have another question?
Yes. So, Arunda, I have this question of this, like this myriad of particle and so. So I'm a bit confused also a bit, because see, whenever we talk about particles, so at least in the first quantization of the kind of presentation you are considering, so it is something to associate with something localized in space, right?
Yeah.
While we don't assign any other physical property to this particle, for example, charge the kind of statistics is followed. For example, if you say all possible possibilities are there to be a particle, but it cannot be true, no? Because we know there are distinctive things like fermion and boson. You cannot have superposition in between because you have parity superselection. So essentially, even to coin this term, saying that, okay, something is in superposition and behind that there has to be a particle, I think is little bit of more
No,
exaggeration.
no, so you, if you agree that to any quantum entity we can associate infinity variety of coherences, that means I could say that there are infinity variety of wave nature that I could associate to a given entity. Okay, if that is so, and if I carry over the wave particle duality, in a very naive way, okay, I'm not saying what I'm saying is right. I mean, I may be wrong, but if I, if I naively carry forward my wave particle duality picture to each of these, wave features, then I will associate to each wave another particle, right? So that is my kind of feeling. I mean,
It's probably
so
better that you even don't term them when there is no confusion. That is a wave function which is as it
yeah,
is.
I mean, yeah, that's the whole point. I mean, this particle, the wave particle duality that we have been trained, we have been taught over so many years could be just a misnomer, the way we imagine this quantum entity as a particle or as a wave could be completely misleading. We don't know what they are. So,
okay. Thank you, Arunda.
yeah.
So it seems there are no more questions. So we should thank the speaker and the speakers all the speakers of this session. Thank you,
Sandeep.
Arun Pati. And we will meet again at 3. Next session starts at 3.
Okay.
So see you all then.